morning, people. I hope you're having a happy new year, delovelies, because I have something new. And it may contain science. Clean energy science. But not clean energy like clean energy. Clean because there's no dirt involved. Energy because we electrified the plants. But I'm getting ahead of myself. The dirt-free subject of our story is hydroponics, the discipline of growing plants without soil. There are tons of reasons to grow hydroponically, from the improved water efficiency compared to soil culture, to hydroponics is far more practical horticulture in space. And there are also a zillion ways to grow plants in not soil. We use a lot of rock-derived materials as our not soil, and things like rock wool, yes, rock spun into wool fibers, to actual sheep wool, to polystyrene packing peanuts, to absolutely nothing at all, because what's more not soil than using not anything and calling it aeroponics? The whole idea with hydroponics is that the substrate itself doesn't matter. Well, it does matter, but unlike soil, it's not where plants get their nutrients or water. Without that responsibility, hydroponic substrate can be chosen based on how well it aerates plant roots, how well it provides drainage, even how pH neutral it is. This control over growing conditions makes hydroponics ideal as a platform for and the subject of scientific study. Want to study genetic regulation of your mouse ear cress under various conditions? Soil bacteria isn't going to be the same kind of confounding factor here. But one other factor in hydroponic substrate selection is sustainability. Rock wool is useful, it's cheap, it's popular in hydroponics for a reason, but rock isn't naturally woolly. And it's energy intensive as hell to melt basalt into a state that it can be woolly. Not to mention, rocks don't biodegrade, so you get what you get, and so on. That is all more than enough rationale for why scientists featured recently in proceedings of the National Academy of Sciences opted to explore different material as hydroponic substrate. They were hoping that hydroponic substrate could be more than just inert and neutral, that with the right substrate in the right conditions, it could actually support or even stimulate plant growth independent of water and nutrition. To accomplish this, they opted for a cellulose and synthetic polymer substrate custom-tuned to the ideal porosity for growing plants' low root systems. Both components of this substrate are biodegradable, which is its own perk, but the two major components each provide different traits to the resulting substrate. The cellulose provides most of the substrate structure, which makes sense since cellulose is the most prevalent biopolymer on Earth and the primary structural component of cell plant walls. The other component is P.PSS. It stands for poly-3,4-ethylene dioxythiophene polystyrene sulfonate, which is why we're going to call it P.PSS and not by its government name. P.PSS isn't a common hydroponic substrate. In fact, you're more likely to find it in your touch screen than in the hydroponic grow-op your roommates got going on in their walk-in closet. And no, Jeremy, no one believes they're tomatoes. P.PSS is a conductive organic thermoelectric material, meaning it conducts electricity and that it converts temperature difference to voltage and voltage to temperature difference. The latter is a neat trick, but P.PSS is in our hydroponics today, mostly for the former, in allowing us to deliver electricity to our plants. Sam, why in Newton's name would you want to deliver electricity to plants? I mean, for science, of course. I mean, we study plants' responses to light, to temperature. We grow plants on the ISS to study the effects of gravity. Hell, we grow them in moon dirt. Why would we not study their response to electricity? Indeed, zapping plants to see what happens sounds like one of those wacky 18th century science experiments that they did back then for the pure YOLO of it all. So much so that, yes, that is exactly what happened. With that unique early scientific combination of inordinate curiosity and reckless disregard for systematic experimental design or human safety, as soon as scientists were able to manipulate and store electricity, they started seeing what happens when you apply electricity to literally anything and everything. Indeed, so many scientists / gardeners / hooligans were out there zapping plants that there is a contemporaneous 500-page anthology of these experiments published in 1783 by Pierre Berthelon de Saint-Lazare called De l'électricité des végétaux, which is French for seemed like a good idea at the time. Since those days of wild experimentation and minimal lab safety, we've learned a lot about the électricité of végétaux, including not just how roots will grow along the direction of an electrical field, but even the endogenous electrical signaling within the plant. But, like 18th century scientists, we haven't studied the subject as systematically as we could, in part because for all the hundreds of years we've been doing it, we don't have an ideal way of zapping plants. We can't always properly confirm that a given electrical field setup is actually zapping the plant or how much voltage is reaching it. We also can't always consistently control the electrochemical consequences of our actions, which means that our zaps introduce confounding variables. But hear me out. What if there were a way to minimize confounding factors while studying plants? One that gave you full control over the experimental conditions, one where... Oh my god, I'm just describing hydroponics again. We've come full circle. And now, our controlled environment has an organic polymer that can conduct electricity. We'll call it eSoil. Yes, the scientists are playing marketing strategist again, but this time I'll allow it. The ideal of eSoil is to create a biodegradable hydroponic substrate that can stimulate root growth through electricity and allow for the scientific study of same. Okay, if I'm being honest, really, I think the idea is to play with plants and P.PSS, since this isn't the first time researchers from this Swedish institution have played with this material. I was wondering, hey, what gave them the idea to study plant electrotropism until I discovered that researchers from this institution also once replaced the lignin in balsa wood with P.PSS to create a, quote, wood transistor, at which point I realized maybe they weren't hydroponics nerds who decided to focus on electricity, they were P.PSS nerds looking for a new excuse to play with their favorite toy. Fortunately, the wood transistor and the eSoil are both incredibly cool, and the actual science in this paper is quite abundant as a reward for playing with said favorite toy. In addition to designing eSoil as a viable hydroponic substrate and validating in barley plants that it provides the plant's roots electrical stimulation as advertised, and that the stimulation has a positive effect on growth. So, in addition to all that, the study's authors also do a short series of demonstration experiments to start to narrow down possible answers to this key question. How? How, for the love of Mendel's pea plants, does electrical stimulation induce roots to grow? Well, there are a finite set of possible things the electricity could be interacting with to create the observed effect. One possibility is that the electricity is affecting the nutrients themselves. Nitrate, for instance, is anionic, and, as the authors show, the plant's electricity buff only appears when the eSoil is positively polarized. Since nitrogen acquisition is typically the plant growth bottleneck, is it possible that the electricity is causing the nitrate to migrate toward the roots and make it easier to take up? Turns out no. The nitrate concentrations in the substrate were identical between stimulated and control plants, so it's not that the electrical stimulation improves nutrient uptake. But when researchers analyzed the plants themselves, stimulated plants had lower nitrate concentrations than control plants. If you have equal concentration in the substrate, but lower concentration in the plant itself, it suggests that the plants have already metabolically converted some of the nitrate into nitrogen-containing biomass, and that's what these scientists think the electrical stimulation accomplishes, improving the plant's nitrogen metabolism so they can use that crucial nutrient more efficiently toward growth. So, how does the electricity improve plant metabolism? Well, that, my delovelies, is a question for future studies, which is scientists speak for, we fabricated the hydroponic substrate, confirmed it could electrically stimulate the plant, proved that it induced growth, and identified the broad mechanism of action. Now please, please, please tell us we have enough to publish this paper. Please, I have a family. So maybe they'll follow up. Maybe these scientists will move on to the next cool project with P.PSS and leave these questions for molecular botanists who specialize in them. But either way, they have shown they've made a fantastic platform to investigate further. I mean, it's not growing plants in moon dirt, but what is? Am I right?